Welcome to this module on cybersecurity verification and validation in automotive systems. In this module, we will explore how cybersecurity testing ensures that modern vehicle systems are secure. This module introduces the key principles of cybersecurity testing in modern vehicles. You will first understand why cybersecurity testing is essential in today's connected systems. Then we will explain the difference between verification and validation, which form the foundation of all testing activities. We will also look at where testing takes place across the vehicle ecosystem and finally how testing contributes to overall system security assurance. This module provides an awareness level introduction to cybersecurity testing in automotive systems. The focus is not on specific tools or detailed attack techniques. Instead, we explain how cybersecurity testing is structured and where it takes place across the vehicle ecosystem. This module serves as a bridge between theoretical concepts such as architecture and cryptography and practical activities such as penetration testing and system validation, which are covered in other modules. Modern vehicles are no longer isolated systems. They operate as part of a connected ecosystem that includes back-end infrastructure, mobile applications, and external communication interfaces. A cybersecurity failure is therefore not limited to a single component. It can propagate across system boundaries and affect multiple layers of the vehicle architecture. This is why cybersecurity cannot be assumed based on design alone. It must be systematically verified and validated across the entire system. A modern vehicle is a distributed cyber-physical system composed of many interconnected components. These components are not independent. They communicate through multiple networks and are increasingly integrated with external systems such as cloud services and mobile applications. From a cybersecurity perspective, this means that a vulnerability in one part of the system can affect other parts. Therefore, security cannot be evaluated at the level of individual components alone. It must be addressed as a system property because vulnerabilities can propagate across interconnected elements. In software-defined vehicles, the traditional architecture based on isolated ECUs is replaced by centralized computing platforms and service-based communication. Functions are no longer strictly separated. They interact through shared services and are continuously updated over the air. From a cybersecurity perspective, this fundamentally changes the problem. Instead of protecting individual components, we must protect interconnected platforms and services, which significantly increases the system's exposure to attacks. Cybersecurity in automotive systems is not implemented ad hoc. It follows a structured life cycle defined by standards such as ISO SAE 21434. The process starts with risk analysis and requirements definition, followed by implementation of security controls. Cybersecurity testing plays a central role in this life cycle. Verification ensures that security controls are implemented correctly, while validation evaluates whether the system can withstand realistic attack scenarios. The outcome of these activities contributes directly to the cybersecurity case, which provides evidence that the system is sufficiently secure. Automotive cybersecurity is strongly driven by international standards and regulations. Frameworks such as ISO SAE 21434 and UNIS regulations do not only require the implementation of security measures, they require evidence that identified risks are properly addressed. This is where cybersecurity testing becomes essential. Verification and validation activities provide the necessary evidence that security controls are correctly implemented and effective under realistic conditions. Verification and validation represent two fundamentally different aspects of cybersecurity testing. Verification focuses on confirming that security controls are implemented correctly. This includes configuration checks, interface validation, and integration testing, typically without executing real attacks. Validation, on the other hand, evaluates how the system behaves under realistic attack conditions. It involves simulating adversarial scenarios to assess whether the system can withstand actual threats. Both activities are necessary. A system may pass verification but still fail when exposed to real attacks, In automotive systems, defining system boundaries is not sufficient on its own. Each boundary also represents a trust boundary. Different parts of the system operate with different levels of trust. For example, external interfaces such as mobile applications or back-end services are typically less trusted than internal vehicle networks. From a cybersecurity testing perspective, these trust boundaries are critical. They define where security controls must be enforced and where attacks are most likely to occur. If these boundaries are not clearly defined, important attack paths may remain untested. In automotive systems, cybersecurity is implemented as a defense in depth strategy. This means that multiple independent layers of protection are used, ranging from hardware security mechanisms to application level controls. The key idea is that no single control can be trusted to provide complete protection. If one layer fails, other layers should still prevent system compromise. From a testing perspective, this has an important implication. Each layer must be tested independently and also in combination with other layers to ensure that no single point of failure exists. Attack surface represents all entry points through which an attacker can interact with the system. However, these entry points are only relevant because they expose valuable assets. These assets may include sensitive data, cryptographic keys, or control over system functionality. From a cybersecurity testing perspective, it is therefore not sufficient to identify interfaces alone. We must also understand what assets are exposed through these interfaces and what impact a successful attack could have. Each identified entry point and associated asset defines a potential test case. Cyber attacks in automotive systems do not occur in a single step. They propagate through multiple system layers. An attacker typically starts from an exposed entry point, such as a connectivity interface or backend service. After exploiting a vulnerability, the attacker gains access to the system and may move laterally across different components. The objective is to reach a critical asset or function where the actual impact occurs. From a cybersecurity testing perspective, it is essential to consider these complete attack chains. Testing isolated components is not sufficient if the attack can propagate across system boundaries. In automotive systems, cybersecurity testing is not performed by a single team or at a single level. The system is composed of multiple layers ranging from back-end infrastructure to ECU level software and hardware. Each of these layers is typically developed and tested by different organizations, including OEMs, suppliers, and specialized security teams. This means that cybersecurity testing is inherently distributed. Ensuring system security requires coordination across all layers and across the entire supply chain. Cybersecurity testing follows a structured, attack-driven process. The tester starts by identifying the attack surface and the assets that are exposed, as discussed in the previous slides. Based on this, entry points are selected across system boundaries, and test scenarios are defined using realistic attack propagation paths. The tester then simulates controlled attack scenarios, evaluating how the system behaves under adversarial conditions. This process ensures that testing is not random but directly derived from system architecture and realistic attack scenarios. Cybersecurity testing in automotive systems requires dedicated test environments. These environments are designed to simulate real system conditions while allowing controlled execution of attack scenarios. Depending on the testing level, this may include ECU test benches, network simulation environments, platform-level systems, or back-end test setups. A key requirement is that testing must be both controlled and repeatable. This is essential for reliable evaluation and for compliance with standards. It is also important to note that cybersecurity testing cannot be performed directly on production vehicles. Instead, specialized environments are used to safely simulate realistic attack conditions. Traceability is a fundamental requirement in automotive cybersecurity testing. Every identified threat must be linked to a corresponding requirement, implemented as a security control, and verified and validated through testing. This ensures that no relevant risk is left untested. From a practical perspective, traceability connects attack scenarios with specific test cases and their results. Without traceability, it is not possible to demonstrate that the system has been properly secured, which directly affects compliance with standards and regulations. The role of a cybersecurity tester in automotive systems goes beyond executing predefined tests. The tester must first understand the system architecture, including communication paths, interfaces, and exposed assets. Based on this understanding, test scenarios are derived from realistic attack propagation paths, taking into account system boundaries and trust relationships. Testing is then performed by simulating controlled attack scenarios, with the goal of evaluating how the system responds and whether security controls behave as expected. Finally, the tester provides evidence that supports verification, validation, and the overall cybersecurity case. This role requires a combination of system engineering knowledge and an attacker-oriented mindset. This example demonstrates how cybersecurity verification is performed in practice. Starting from an identified threat, a cybersecurity requirement is defined to mitigate the risk. This requirement is then translated into a verification activity, where the system is tested under conditions that simulate the identified threat. The key point is that verification is not performed randomly, but is directly derived from system risks and requirements. This ensures that all relevant threats are systematically addressed through testing. This slide continues the previous example. The cybersecurity requirement that was defined is now translated into a concrete test case. The test is designed to simulate the identified threat and to verify whether the implemented security control behaves as expected. This illustrates how requirements are made testable and how verification ensures that the system is protected against the identified risk. This test case represents the final step of the example introduced in the previous slides. Based on the identified threat and the defined cybersecurity requirement, a concrete test case is created. The test simulates conditions that reflect the threat scenario and evaluates whether the implemented security control behaves as expected. This demonstrates how cybersecurity verification is performed in practice, from threat identification through requirement definition to executable test cases. This slide continues the test case and focuses on its execution and evaluation. The tester performs the defined steps and observes how the system behaves under the simulated conditions. The key aspect is not only executing the test, but interpreting the results. The tester must determine whether the system response meets the expected behavior and whether the security control is effective. This step is essential for validating that the identified risk is properly mitigated. This example illustrates cybersecurity verification at the software implementation level. While the previous example focused on system-level verification, this case demonstrates how vulnerabilities can exist directly in software components. Here, a command injection vulnerability allows unauthorized execution of system commands. The purpose of testing in this context is to identify such weaknesses and verify that input validation and secure coding practices are correctly implemented. This highlights that cybersecurity verification must be applied at multiple levels, from system architecture down to software implementation. This example shows a typical environment used for cybersecurity verification. Testing is performed in a controlled setup that includes an attacker system, a target system, and a network environment that simulates real vehicle communication. Tools such as penetration testing frameworks are used to simulate attack scenarios, while monitoring tools allow observation of system behavior. This highlights that cybersecurity testing is not performed directly on production systems, but in dedicated environments designed for safe and repeatable evaluation. This slide shows how artificial intelligence can support cybersecurity verification activities. AI can assist in analyzing complex systems, identifying potential attack paths, and generating test scenarios based on system behavior. It can also support evaluation by detecting anomalies and patterns that may indicate security issues. However, AI does not replace expert-driven testing. It supports the tester in handling system complexity and improving test coverage. While AI can support cybersecurity verification, it also has important limitations. AI does not fully understand system architecture or context, which can lead to incomplete or incorrect test scenarios. The results generated by AI must always be validated by an expert. Most importantly, AI cannot take responsibility for security decisions. This means that cybersecurity verification remains an expert-driven activity, supported but not replaced by AI. Cybersecurity testing in automotive systems is performed by different specialized roles. Cybersecurity test engineers focus on verification of implemented security controls and system interfaces. Penetration testing specialists simulate realistic attack scenarios to evaluate system resilience. Other roles, such as architects and auditors, define requirements and assess compliance, but testing itself is performed by dedicated technical experts. This highlights that cybersecurity testing is a specialized engineering activity within the overall cybersecurity lifecycle. A strong automotive cybersecurity tester combines system engineering knowledge with an attacker mindset. The tester must understand vehicle architectures and communication protocols, as well as security mechanisms implemented across the system. Equally important is the ability to think like an attacker, identifying attack surfaces and designing realistic scenarios. Cybersecurity testing requires understanding how complex systems behave under attack conditions. The cybersecurity case represents structured evidence that the system is adequately protected against cybersecurity risks. Verification and validation activities contribute directly to this evidence by demonstrating that security controls are correctly implemented and that the system resists realistic attacks. This evidence is required for regulatory approval and vehicle homologation. This module introduced the fundamental principles of cybersecurity verification and validation in modern vehicles. Cybersecurity testing ensures that security is not assumed, but demonstrated through evidence. In practice, this requires deep technical expertise and controlled environments, which are addressed in advanced training.